Beach ball? No. All right, so 3.1 example 10, we're gonna finish the notes here today. When the EVT does not apply, and by the way, the EVT applies when? A continuous function on a what type of interval? Closed interval, yeah. If the EVT does not apply, we could still have both a max and a min. There's no guarantee, but we could have both of them or one of each or possibly neither. You might still be required to find max and mins when the EVT doesn't apply. So how do we do that? Well, we can't really use the closed interval argument, can we? Because that only works when the EVT applies. So we have to find the extrema some other way. And if you remember how we did it at the beginning of the section, it was pretty darn easy to start because we actually were just doing what? Looking at a graph, and we're like, I spy the high point. I spy the low point, right? It's easy. So I think we can all agree that if we could generate a graph of the function, we could answer questions about extrema a little bit easier when the EVT does not apply. And part of the usefulness of the derivative combined with what we've learned about function values and stuff is so that we can generate graphs of these unfamiliar functions without a calculator, kind of like we did on the warm-up. All right, find the extrema of each of the following functions over their domain, and it says by sketching their graphs. Well, we really don't need that hint anymore, do we? Because we've talked about it, and it now just becomes part of what you consider on a regular basis, right? So I'll get rid of that. Okay. Here we go. Sketch the graph. I guess you could do what you did back in Algebra 1, remember? Remember that? When you first learned how to graph functions, independent variable, 0, 1, 2, 3, 4, plug them in, get the y values, plot them, connect the dots, and go from there. That wasn't very efficient, but it was a good way to kind of introduce you to graphs. We're going to do something better than that. The first thing that we probably want to do is find the domain. Right? We want to do that first. We want to avoid dividing by 0. We want to avoid square roots or fourth roots or even roots of negative numbers. Of course, we want to avoid logs of anything that's not positive. And with piecewise functions, we always have to be careful to see where it's explicitly defined or not defined. Do we have any of those things going on here? We have two of them. Yeah. We have a square root with a variable underneath it, and we have a variable in the denominator. So kind of taking you back to the pre-cal days, I would look at the radicand first. You could say it's greater than or equal to 0, and then you could set the whole thing not equal to 0 to figure out any values that cause 0. But if you recall from pre-cal, you can do a 2-for-1 here. Because the denominator itself is in the entire radical, if you just say greater than 0, that'll not only prevent division by 0, because the square root of 0 is 0, but that leaves you a 0 in the denominator. It'll give you all the values that work in the radical as well. So you can do it with a single inequality. Now, this being a nonlinear inequality, we cannot solve this one algebraically. We have to solve it by some other method, either by testing intervals or graphing it, which I think is probably the easiest way to do it. So if we graph it, I would probably factor it. It's a difference of 2 squares. So we'll have a 2 minus x times 2 plus x is greater than 0. And, of course, the x-intercepts are 2 and negative 2. And you could probably figure that out just by looking at it. Now, if I sketch the graph, just a real quick sketch. Negative 2 over here, positive 2 over there. The graph opens down, and the vertex is at the origin. And now we want to know for what values of x is the graph strictly, greater than 0. That's going to be everything between the x-intercepts. Everything between, strictly between. So the domain of our function is going to be the set of all x such that negative 2 is less than x is less than 2. And of course, you could also write that as an interval. And in this context, it's not an ordered pair. Alrighty, that's good to know. What else can we grab from this function kind of for free without BOTCing? Intercepts, good. We can look for the y-intercept. In general, the y-intercept is the easier of the two to find. How do we find y-intercepts? Plug in a 0 for x. So that would be f of 0. And if we plug in a 0, 0 is in the domain, right? We get 1 over the square root of 4, which is Is it 1/2 or plus or minus 1/2? Right. No, we don't do plus or minus here because the radical's already there, and we take the indicated root as positive. You only do plus or minus when you introduce it to solve. Good. So it's 1/2. Well, you know what? I have enough information now to start a sketch. You want to kind of keep the sketch going and maybe just add to it as you find more information? I've got one of the pieces. I know it crosses at 0, 1/2. So I'm going to call that 1/2, and there's my dot. Yay! Now, -2 to 2, I'm going to go ahead and call this -2. I'll call that +2. I know it doesn't live to the left or right of there. What else can we do here? X-intercepts. Do we have any X-intercepts? That's when the whole thing equals 0, but being a fraction, it's equal to 0 when the what 0? The numerator. Is the numerator ever 0? No, the numerator is always a what? A 1. It's 0's next door neighbor. That doesn't make it 0, even if it house sits for 0. So there's no X-intercepts. This thing never touches or crosses the X-axis. Good to know. The domain's all real numbers? No, it's not. Is it continuous between -2 and 2? It is. And so if there's no X-intercepts and it's continuous, this graph has to live exclusively either above or below the X-axis, right? Does it live above or below? Oh, it lives above. We already have a value. So I know it's got to live now. Now I'm kind of restricting it. It's got to live somewhere in this vicinity. All right, cool. Let me get rid of that because that's not needed. Okay. So, no sense talking about the end behavior here, right? Because it doesn't have end behavior. It only lives at -2 and 2. How about symmetry? Is symmetry going to be helpful? Yeah, in general it is. Let's review symmetry very quickly here. The test is to replace x with -x, right? And if you get the exact same thing, that is if all your negatives go away because you're like squaring them or raising them to the 4th power or any even power, then the function is an even function and it has y-axis symmetry. But if you end up with the exact opposite of what you started with, then all the y values are the opposite, and you get an odd function that has origin symmetry. All right, so does this one have any symmetry? If you replace this x with the -x, the first thing you're doing is squaring it. That means it's going to be the same as if you plugged in a positive x, right? So this graph has y-axis symmetry. It's an even function. That's neato. So now if I know what it looks like in quadrant 1, I've got the whole graph because that's what it is in quadrant 2. Or if I know what it looks like in quadrant 2. I guess the only real question is what's happening as we get close to 2? Like, what's it doing? Is it going up here and, like, stopping and saying, hey, how's it going? And then by symmetry, hey, what's it doing? Is that what it's doing? It's approaching 0. So is it going down and going like that? And then like that? This is all without calculus. Let's do this. What would be the limit as x approaches 2 from the left-hand side? Right? That would be interesting. That would reveal the behavior of the graph as we approach the cliff of 2 where it doesn't even exist. Well, pick a number just to the left of 2. Well, let's come over here to the graph. If I pick a number just to the left of 2, my radicand, right, which is this the graph of, is going to be some tiny, tiny, tiny small positive number. Agreed? Okay. If I then take the square root of a very small positive tiny number, I'm going to get a smaller positive tiny number, right? Even smaller yet. And what is 1 over a very small number? What is the reciprocal of a very, very tiny small positive number? A very big positive number known as infinity. Okay. So that means that there must be a what at 2? A vertical asymptote. That's pretty special. That was the definition of a vertical asymptote. If the limit as x goes to some finite x value from either side equals plus or minus infinity, because there's a vertical asymptote there. Now I'm guessing that the graph looks like that. Okay? I'm guessing. And if it looks like that on that side, then I'm guessing it has to also look like this. Now the reason I say I'm guessing, I know there's no x-intercepts, but does the graph dip below 1/2 and then go up? It could. And that's significant because if it did dip below 1/2 before it went up, I would actually have an absolute max right here. Yeah, I'm saying I'm looking at the vertical asymptotes as I say that. Do we have an absolute maximum in any case? No, because it increases that bound on both sides. But my absolute minimum could be something other than 1/2, and if I have 1, it's going to occur over there as well. So how can we use calculus to help us decide if it actually does dip down here? The derivative, because if it did come back down, it would have to turn around continuously, and we would have a horizontal tangent line there, right? Which means the derivative would equal 0 at that number on the right, the symmetric number on the left, and at 0, where we would have a local max. So let's go ahead and find the derivative very quickly. And I would rewrite it, I hope you would too, as 4 minus x squared to the what power? Negative 1/2. Cool. Now, the chain rule. Chain. Come back. The end. To the what power? Negative 3/2. And recall I mentioned when we did the chain rule that is probably the most common mistake that students make. They tend to leave that off. Times the chain rule, negative 2x. All right, so if I simplify that, just to make it easier to work with, I notice that a negative 1/2 times a negative 2, what happens? They divide out, and I'm left with an x over the bottom becomes the square root of 4 minus x squared cubed. We know the answer now, don't we? If I set this whole thing equal to 0, it's going to be when x is equal to 0, and that's the only critical value that I have. So that's the only horizontal tangent that I have. So indeed, the graph must look like that. Yeah. So we've got the answer now, right? We only had to bust out the calculus for that one little confirmation. And now we have the answer from all the other information. So let's go ahead and say F has a minimum of y equals what? 1/2 at x equals 0. And F has a max or no max? Yeah, no max. All right, there you go. Kind of fun. Kind of fun. If this was a multiple choice question and you just didn't BOTC, but you were guessing that the graph looked like that, you'd be right. You'd be right. Always, if you guess correctly, you'd be right. Always. Yeah. I mean, how do you even bubble? How do you hold a pen when you're like that? And I don't know. I mean, you probably get good at it after a while. Yeah. But then picking the nose thing, I still don't know. Yeah, your nostrils would be like those guys that have spacers in their ears. Here's what I'm going to do. I'm going to cut you loose on this one. You can do this one. Use your own powers. Let's first of all look at this. We're finding the absolute max or min on the entire domain. Does the EVT apply? Well, let's see. To the left of 1, it's a parabola that opens down. So that goes how far to the left of 1? Does that graph of the parabola go on forever to the left? Yeah, it does. We have x plus 2 going out to the right of 1. That's continuous everywhere. So do we even have a closed interval? Now, if we're talking about over the domain, and the domain is all real numbers because this function is defined everywhere, it doesn't matter if it's continuous or not. There's no closed interval. The domain is infinite. Now, we could determine if it's continuous, right? Pretty easily. Where would be the only place we would need to check? At 1. Let's just mentally do it in our heads. What's the limit from the left of 1? 3. What's f of 1? 3. So we got 2 to the 3 right there. What's the limit from the right of 1? 3. Hot diggity dog. Does 3 equal 3 equal 3? It does. So is f continuous there? Yes. Let's quickly review how to determine if it's differentiable there. We know it's continuous. Does that mean it's differentiable? No. We can either do A, the alternate form definition of the derivative. No, thank you. Or, since we now know it's continuous, we check for continuity first. Let's do this very quickly. Let's come up with a piecewise derivative. And this is review, and then I'll cut you loose in the max-min question. You get a negative 4x, and that's going to be to the left of 1, and you get 1 to the right of 1. Now, notice when I define the derivative, I didn't say anywhere equal to 1 because that's what I want to check. If I say that the derivative is equal to 1, it's somewhere I'm saying it's differentiable at 1. What would be the slope from the left of 1? Negative 4. What would be the slope from the right of 1? 1. Is it differentiable at 1? Absolutely not. It's continuous there, but it's not differentiable. Okay, that's a review question. You go ahead now and find, if they exist, the max and mins. And I'm going to kind of doodle up here while y'all do that. Doodle up here while y'all do that. Yeah, I'll doodle mathematically. It'll be meaningful doodles. Remember how easy it was in the opening of this section just to be able to look at a graph and determine an absolute max or an absolute min. So nice to have graphs, especially the ones that we generate ourselves. Here's an interesting result coming off here. You have it going up forever. If it did go up forever, then there would be a minimum there, but it's actually a what? So it would actually turn back down. Interesting. Yeah, you really want to take inventory of what the pieces are. It should be, if it's like a piecewise function like this, it'll either be recognizable functions like parent function transformations or something that you could do some analysis on like the previous one. Is that das Wirken? What? Nope. Nope. Oh, okay. Okay. Are you finding? Oh, you're finding the X-Intercepts. Right. Yeah, that's fine. Yeah, there's a lot of it. Yeah, you can find a lot of information. Well, yeah, I mean, it depends on what the question is asking you. If it's asking you for to sketch like an accurate thing, you might want to know the X-Intercepts. But if we're just after the absolute max or absolute mins, it's kind of like that old show, Name That Tune. You want to try and name the tune in as few notes as possible. Just try and get the shape of the graph. What's that? If you're going to see where, yeah, you could do that. And guess what you're going to get? You're going to get, because if you're looking at that piece, what are you going to get? X equals 0. When you take the derivative? Yeah. And look at the graph that I have up there. That's consistent, okay? Because if you recognize that 5 minus 2x squared is really just a parabola that opens down, the negative 2 reflects it down and stretches it, and the plus 5 moves it up to 0, 5. So that's where the vertex is. So knowing that is helpful. Yeah, but what you're doing is fine too. Again, you can use symmetry here. You can use y-axis. You can use x-axis. You can do end behavior. You can do all that stuff for a piecewise function. But what is actually necessary in order to answer our question? We were looking for the absolute max and min. I know then that it's, again, and I mentioned this just a little while ago, that this is a parabola. That's important to realize it's an x squared with a negative coefficient. That means it's a parabola opening down. The 2 stretches it vertically. We don't really ever show that, but the 5 in front is really important because this graph doesn't shift the parabola left or right. It shifts it straight up. So the old vertex was at 0, 0. Now it's up at 0, 5. And 0 is in our defined interval. It's to the left of 1. So we've already decided that it was continuous at 1, but if you hadn't, you would plug in your 1 from the left and right, and you would plot that at 3, and it's an open circle. So to the left of 1, 3 now, you go ahead and complete the graph of what the parabola would look like. If the vertex is at 0, 5, you go up to that point, and then remember you turn the corner and you decrease down for when? Ever. And then to the right of 1, it's the line x plus 2, which has a what type of slope? Positive. And that's also significant because what does that mean in terms of a max and a min for this graph? There are none. There's no max because it decreases without bound. There's no min. There's no min because it decreases without bound. There's no max because it increases without bound. Now, are there any local extrema? Yes, we have a local max of 5 at 0, and we have a local min of 3 at 1. And notice at the local max, the derivative is 0, and at the local min, the derivative is undefined. Yeah. Now, what if that line had started at the point 1, 3, but the slope had been negative 1? Then we would have an absolute max at the local max, right? The absolute max would be 5. Yeah. So the slope of the line does make quite a bit of difference. What if that line had been moved down here? Yeah, we'll get rid of that. What if the line had moved down there, and I guess that would be an open circle? That wouldn't change the absolute max or absolute min, would it? But would this still be local min or a local max at x equals 1? No, it'd be a local nothing, right? Because you go to the actual dot, to the left you would have bigger values, and to the right you would have smaller values. So it wouldn't be a local min anymore. However, whoops, what if this was actually moved up? Okay. Now there's still no absolute max, absolute min. Would this still be a local min? Yes, we would still have a local minimum of 3 at x equals 1. Yes. Yeah, if the instructions say to do so. Yes, the whole next section, or 2 sections from now, is all about local extrema and the first derivative test. For this specific problem, it just said find the extrema. And so that means what type? Absolute or global. Yeah, it doesn't. If it wanted you to find the local extrema, it would say find the local extrema or the relative extrema. Remember, if there's no qualifying word in front, we assume absolute/global. All right, sometimes we need to use our calculator's number crunching ability to solve equations by finding x-intercepts for us. Okay. Use your calculator's equation solving capability, not just its max-min finding ability, to find the extrema of this function. Okay, so here we go. We're on a closed interval from -1 to 1. Is this function continuous on that interval? Do we have any square roots in that problem? Do we have any logs in that problem? Do we have any denominators in that problem? Oh, there is one. It's x over e to the positive x. Is e to the x ever 0? No. E to the x is never 0. It approaches 0, but it's never equals 0. So we never get division by 0. So what's the domain? All real numbers. So this function is continuous on a closed interval. Are we guaranteed a max and a min? By the EVT, yes. So let's go ahead and find the derivative to find our critical values. F prime of x is going to equal the derivative of x e to the negative x requires the what rule? Product. So we got 1 times e to the negative x plus x times e to the negative x times the chain rule, -1. Which, of course, you could pull out front if you needed to already. And then the second term, minus 2x, that's just -2. All right, so if we could we do with that? Well, we could bring the negative out front and do that. Is this ever undefined? Let's just answer that question first, because that's the one most students overlook. We get critical values where the derivative is undefined if the function is defined. We already said the function is defined everywhere. Is the derivative ever undefined? No, for the same reason the function was defined everywhere. The two e to the negative x's are never 0. So there's no possible cusps or vertical tangents here, right? But there could be horizontal tangents. Now, because I'm only going to use this once, find horizontal tangents, I'll go ahead and set that expression equal to 0. Now, here's where we kind of need the calculator's help. Algebraically solving that one is not going to work. Now, I know what you're saying. You might be saying, but can we factor out an e to the negative x from there and then bring the 2 across and set it equal to 2 and then set both of those equal to 2? Does that work? No. You know why that doesn't work? Because 2 is not 0. It only works with 0. It's the zero product property. Two things multiplied together giving you 2. Neither one of them necessarily have to be a 2. Right? For instance, 4 and 1/2. Neither one of them are 2. But it only works with 0. So can't do that. And I see that sometimes. So I guess we try to factor this one all together, but it's not going to work. If that had been like e to the negative 2x, then maybe it's a quadratic, but that x, no. So guess what we do? We go to the calculator, and it's going to help us. So we're going to graph this in y1. We're going to graph this in y2. And this will be the last problem that we do. And then I guess the announcements will come on, and then I'll give you your test, and we'll call it a day. All right, so graphing that, and this is what we're going to be doing a lot of later in the year, when we get to chapter 6, especially. Okay, so e to the negative x, that's second ln to the negative x, minus x, oops, I'm not used to this yet. You got to get out of the exponent. Click to the right. Okay, now we're back on the ground floor. Minus x times e to the negative x again. Click to the right, and minus 2. Now, if you had an equation where it was like equal to 2, I would still encourage you always when you're solving an equation to get everything on one side and set it equal to 0. And the reason being, again, is because you're looking for points of intersection. And when you set it equal to 0, you know where y equals 0 is, right? It's the x-axis. You don't have to like hunt high and low to see where the graphs happen to cross each other. And if you graph 0 in y2, your calculator can find points of intersection a little bit faster than it can find X-intercepts. Now, here's the other thing you want to be careful about. On the window, we are looking for this problem specifically between -1 and 1. You don't want to look outside that window because there could be other values that are higher and lower, and we don't want those. Now, because we're looking for the X-intercept, I would always encourage you to put your y-min and y-max to something small but symmetrical, -3 to 3. That way, if the graph kind of doesn't rise up above or below the x-axis very much, which they do create problems, you know, like that, so that you think it crosses but it only bounces or whatever, you've already kind of got it stretched out. And now you're looking for X-intercepts. Here we go. Ready? Graph. La, 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 la. Does it cross? Does it cross? Oh, yes, it does. Do we have another one? Is it going to turn around? Oh, no. No, it didn't. All right, so because we graphed the y-axis, there's only one point of intersection. Here's what's nice about it. Go to second trace, and you're going to choose option 5. And now all you got to do is find the enter button. I'm on the enter button. Close your eyes and say enter, enter, enter. That's nice. And like magic, it gives it to you if there's only one point of intersection. Okay, so notice it has it as x equals. Here's another thing that we're going to be doing a lot of. If I go to the home screen, second quit, notice if I hit x, there it is. It stores that value in x. And if you think that you might need to use that later on, go ahead and hit stow as alpha A. Stow as alpha A, and there it is as A. And then you can go back to the graphing screen and find another one if you want. Now we have that decimal answer stored completely. If we need it. So what I'm going to do over here then, to find the absolute max or min, I'm going to now evaluate my function at each of them. So I'm going to go f of -1, f of 1. And by the way, I would need to declare my answer here. X equals -0.37. How many decimals do we need to report? You always report 3, and you can round or truncate. So 0.374 or 0.375. Either one works here. Now, you never use that rounded number for any subsequent calculation. So sometimes I like to put the ... at the end of it, which just tells me there's more to that number than that, and I need to use the actual number that's stored when I'm calculating anything. So I've basically solved the equation. I have my critical value. Is it in my interval? Of course it is. You know why? Because I had my calculator set to that window only.
Please turn your TV on to channel 4 for this morning announcements.
Now,
you may also watch these morning announcements at nbhstv.com.
Here's the other advantage of storing it on your calculator as A. On your paper or iPad, if you store it as A, you can call it capital A. As long as there's not already something else that you're calling A, like area or whatever. And now, on your analysis, you could just say f of A instead of f of -0.374. Okay, so you want to plug all those back into f. Is there a quick way to do that? Sure there is. Okay. Do we need the derivative anymore? No, we don't need the derivative anymore. So you can either get rid of the whole thing or salvage it. I'm going to salvage it. X e to the -x minus 2x. So if your equation is kind of ugly, you can put it in y1. And then, of course, from the home screen, vars, y vars, function 1. Or you can go to the shortcut there, alpha trace of, and here we go. Let's plug in our -1. Enter. And I get that number there. Now, you do need to report that number, that you're showing that you're reporting that. So that would be -0.718 to 3 decimals. Now we do the same thing. I'm just going to hit second enter. That recalls it. I'm going to scroll back over here, and in place of the negative, I'm just going to hit delete. That should evaluate now the function at 1. And I'm letting the calculator do all the heavy lifting for me. So that's going to be -1.632. And then finally, second enter recalls it. I'm going to scroll back here on top of the 1, and guess what I'm going to type in? Alpha recalls it after alpha A, alpha math. And since I stored it as A, there it is. Now you could have also done y1 of x, because it's still stored in as x. But you'll notice later on, we actually find multiple values that are ugly decimals. And every time you find a new one, it overwrites the old one. So you want to have it stored before you find the new one. Now you can just write that down, 0.204. And again, it's super important to write down at least 3 decimals. Because let's say you left off the 8 on the top one there, you lost a point. Okay? You got to report 3 decimals round or truncated. Now we can answer the question, right? F has a max of what? 0.204 at, now I'm going to go back and use the actual x value here, at x equals -0.374. And f has a min of what? -1.632 at x equals 1. There you go. That's how we're going to be using our calculator. It's a very useful device for storing numbers, finding numbers, and in terms of like how to get credit on a calculator free response, everything that I showed you right here would be the bare minimum that you would need to show. As long as you're showing f of -1, f of 1, f of a, and you have a labeled, that's it. You don't have to do anything else. Full credit, 100%. Pretty nice. All right, we're going to stop there. That's the end of the notes. We'll make the worksheet due on Monday. Okay? Yeah, Monday, because there's something else due tomorrow, and I'm going to give you that assignment now.